good evening to all. I think all are joined now. So we can start today's. So today we will start with the design part. So last time we have discussed the analysis, basics of the analysis. And once we do the analysis of any structure, then after that, whatever forces we get through the analysis, that is bending moment, shear force, or axial force in the column, we design the members. So next step is design. So I just want to ask you, what do you mean by design? What is meant by design?
Find out the sizes of members and reinforcement.
Yes. So finding the sizes. Let's say we are talking about RCC design for the time being. So if you are doing the RCC design of members, you're finding the sizes of members. Okay. So whenever you design either beams or slab, or you design columns, or you design footings, whatever. So whenever you design, you arrive at a size of a member first. Then you put the reinforcement into that. So putting the reinforcement. So I can say, if let's take the example of beam, then deciding this width. So what should be the width for that beam to take whatever bending moments are coming in the beam. So you know that in beam we get bending moments, we get shear forces in general. In column we get axial force, we get bending moments, and we get shear forces. In footings we get bending moments and shear forces. And in slab we also get bending moment and shear forces. Slab is similar to generally beams. Okay, footings and slab are same. Column is having axial force also, compression additional, apart from the bending moment issue. So these are the forces we get from the analysis, and we design these members for these forces. And designing means deciding the size B and D of this say beam, for example. Then putting the steel, so it may be main steel required for the bending moment, and there will be stirrups required for the shear force. So stirrups we provide for resisting the shear force, and this red main reinforcement we provide for the bending moments coming in the structure. And also we provide, so bending moment, all of you know that whenever we call bending moment or moment, it is force into distance. So it may be tension into distance, or it may be compression into distance. So this RCC member comprises of materials. So first we provide the steel, and then concrete section is done. So this material is concrete material. So this all material is concrete. So whenever we design, we can say deciding the sizes of member, deciding the reinforcement, and deciding the material also. So selection of material for the member, selection of material. So these are the criterias in the design. First of all, this is mean by the definition, we can say design definition. Now if you want to arrive at the sizes, proper sizes, so what is required? So how will you decide the size? How will you put the reinforcement, or how will you select the material? So let's say generally we in buildings we are proposing RCC material. So why steel is provided in the concrete beam?
To take the tension coming in the concrete,
Yes,
because
because
concrete is weak in tension.
so concrete is weak in tension, and as I know that whenever there is a bending moment in beam, it carries tension and it carries compression also. So there is always a compression and tension in the beam, concrete RCC beam, we can say. So to take this tension, we are providing reinforcement because concrete cannot take this tension. But for compression, we are using the concrete material. So generally, see, there is a neutral axis. And let's say the lower zone is having tension zone, we can say, due to the bending moment, let's say. Then we ignore this concrete part, lower part, and we provide this reinforcement for taking this tension. And the upper part we use for the taking the compression, and which is coming through by the bending moment. So all of you know that, see, bending moment, I think now everybody is clear about bending moment. So if we have this kind of beam, then due to the load, it will bend. And due to, let's say this is a simply supported. So there will be tension at the bottom. So this will have a tension, this will have a compression. And as this bottom zone is going in tension, so we will provide tension reinforcement. And for this top zone, as it is in compression, we will provide the concrete within that. And these two bars we are providing additionally just to hold the stirrups. So generally we don't take this part into consideration for compression. We ignore it for compression. So that is the meaning of design, we can say, in totality. Now, what are the aspects we check in design? Important aspects. If you check that, then we can say the design is safe. Yes.
On deflection check.
Yes. So I can say there are two checks. One is a strength check. Whenever we design, these are the two criteria which we take into consideration. See, any design, it may be concrete, it may be steel structure, or it may be timber or whatever. So we check strength, we check deflection. So whenever you check strength, what do you check actually?
Bending moment, shear force.
Not bending moment, shear force. They are coming from the analysis. Whenever I say strength check, I check the stresses actually. So the actual stresses coming in the structure due to this bending moment, shear force, and axial force. So actual stresses should be less than permissible stresses. And these are given in IS code. Permissible stresses you will find in IS code. So that is nothing but a strength check. And what is deflection check? Actual deflection. See, actual stresses are coming due to the loads. And actual deflection is also due to the loads, right? So actual deflection should be less than permissible deflection, and which is given in IS code. So this deflection criteria, we call this as a serviceability check. So you know that there is a in IS 456. So which code we are using? IS 456 for RCC. So in IS 456, we have limit state of serviceability. And this is nothing but we check the deflection, and there is one part that is limit state of collapse, which is nothing but strength criteria, strength check. So these are the two checks we do in design. So this is very important. And as these two checks are important, that means you should know how to calculate the deflection and you should know how to calculate the stresses in the member. Okay. So what are the important aspects? We have seen the size. See, the words are important. The size. Size means width and depth. That is the size. Then reinforcement, selection of material. Then stresses. So this word is also important. So stresses. So what is meant by stress and how to calculate the stresses. Then where to find these permissible stresses. Then how to calculate the actual deflection. So calculations. And whenever you call the deflection, there are two words. One is the stiffness. So whenever you say design of any member, the important word is stiffness. Stiffness is a very important word. It is a property of section. Okay. It is a property of section. So mainly I can say stiffness is more related to what? Is related to this stiffness. Moment of inertia. So you should know what is meant by moment of inertia and how it affects the design. So the implications you should know, implication of moment of inertia on the design. Implications on design. So you should know what is meant by I, how to calculate that. Because as the stiffness increases, what happens? That we will study. Okay, no issue. So in general, we try to understand the design. So these are the only two things in design mainly. But whenever I say only two things, there are a lot of study you need to know. For example, strength means stresses. You should know how to calculate stresses. What is meant by stresses? What stresses comes in beam? What stresses come in column, and so on. Then you should know how to calculate the deflection. What are the formulas, and what it is depending on. And so on. Okay, so these are the important aspects in any design. And whenever you design, what parameters you should consider? Already we have discussed this, but let me again refresh that whatever your design is, it should be strong enough. That means strength criteria. It should be, we can say, serviceable. So deflection should be within limits. Then definitely strong, and definitely it should be stable. For beam design, you are requiring this size. Say for example, 230 by 450 is sufficient size for the beam, but you are providing the size of the beam as, let's say, 230 by 600. Okay, so unnecessarily you are increasing the material, additional material, right? But your design requirement is this much only. So here I can say interaction capacity your is let's say near to 95%. Whenever I say interaction ratio is 95%, that means I'm using 95% material, whatever material we're. So this additional material will waste, because all of you know that this area into length of the beam will be the volume of the concrete. So let's say you are putting additional, ये कितना है 0.15 समझो, and this is additional I am putting 0.15 meters. Let's say this is 0.6 meter, 0.23. Let me put it in meters first. So I am putting 0.15, समझो 0.15 meters height into 0.23. एक काम करेंगे, कैलकुलेशन के लिए मैं 300 लेता हूँ. ये 300, let's say I require 300 by 400 actually, but I am putting 300 by 600. So 0.15 into 0.3 कितना आएगा ये? Correct है ये?
Yes,
Yes,
sir.
sir. Yes,
So it
sir.
is meter square. Now let's say in your building, you are having different beams like this, and the length of the beam is let's say including all, say total 200 meters. Okay, so ये कितना आएगा multiplication?
9 meter cube.
So it will be 9 meter cube. So you are putting extra 9 meter cube material because you are not designing, maybe not giving much importance regarding the cost and all. Let's say you are feeling insecure and you are putting additional concrete. And 9 meter cube into general rate of the concrete is material and let's say shuttering material. Both material rate, I can say today's rate is 10,000, let's say, rupees per m cube. Okay. So how much is the cost? Yes. 90,000. That means you are putting extra 90,000 rupees. So it is a really not good solution. Unnecessarily don't put extra material. So unless until your design is cost effective, it is really not good design, I would say. So good design means it should be strong enough. So strong means the permissible stresses, stresses should be less than permissible stresses. Then there is one more thing in strong, that is it should give warning to us if it wants to fail. Warning. Let's say there is a generally we are providing let me give that example first. So okay, I'll just take this part ahead. So it should be cost effective for first cover this. So if you are putting such kind of additional material unnecessarily, then it will, the cost will increase and it is not good design. Then it should be strong enough to take the stresses and it should give the warning before it fails. Then the deflection should be less than the permissible limits. It should not collapse. That means it should be stable and it should look beautiful also. This is very important part. Okay. Beautiful means architectural part. Aesthetics is architectural part. All of you know that this size, whenever I say deciding the sizes, design means deciding the sizes. That means the size should also look good architecturally, aesthetic point of view. So the size selection is also important whenever you take any decision regarding the size of beam, size of columns. The orientation and size should be such that the structure will look beautiful in all respect. It may be elevation, it may be internal part, interior part. It should look beautiful. The arrangement of the material, the size of the material, orientation of the material should really give the beauty to the structure. Then and then we can say design, because design, all of you know, it is nothing but a creative phase. Creative means I say art. We have already discussed on this point. So definitely whenever I say creative or art, it should follow these parameters of the creativity or art. Art means beautiful. Otherwise, we cannot say it is an art if it is not beautiful. So this is an important point. So these are the important aspects of the design. Now, I was discussing this. It should give warning before collapse. Do you know this meaning? What is mean by that? Do I mean by this? Should give warning before collapse.
Yes, sir.
So what do I understand by this?
Means the section should be under reinforced.
Okay, so
So
let's not
that
go in
the
detail. Huh.
steel fails first and concrete fails later.
Yeah, okay, no issue.
There is not sudden failure. There should be a
Yes,
indication of
there,
sign that it will going to fail in future and like that.
correct. So there is no sudden failure. So let's say we have a beam here. Okay. Let's say this is your real structure. You can say it is RCC beam or column, whatever it may be. And there is a load. Let's say there are people, there may be some furniture or whatever. I'm just not drawing the upper floors. There is a furniture, there may be storage of material, cupboards. So there are a lot of loads which are on the beam, let's say. So if this is the case, and we know that we have designed the structure for these loads, let's say for some live load, let's say I will design this beam and slab for live load of 2 kilonewton per square meter, for example. So generally we design that, and let's say uh, just a moment. Now, due to some reason, let's say in future, the client is not aware of the structural design and all, and what happened by mistake or due to his lack of knowledge, lack of awareness, he has put lot of load. Let's say he has put the storage, uh, and storage was having almost 6 kilonewton per square meter, 6, 7, whatever, or 10 kilonewton per square meter load. And what happened due to the storage? Let's say your structure got collapsed. Okay. So let's say your beam gets collapsed. Instead of this, let's say, yeah, ऐसे कुछ तो हुआ. Say just ये fail हो गया ऐसे कुछ तो. See, it got broken down and then it fell down. Everything. Okay. So you can see this beam got failed. And fail means we can say brittle failure, or we can say catastrophic failure. Without understanding anything, let's say there are people who are sitting here. Let's say you don't know. These people are using this uh, room, and immediately without any understanding it got collapsed, and there is a problem, say loss of humanity, let's say. So this is not a good design, no good design we can say, because the brittle failure is there and it has not given any warning before collapse. So it happens. So if there is no enough reinforcement within the structure, and all of you know that concrete is a brittle material, and if there is problem in putting the reinforcement, if you are not providing enough reinforcement, then it will collapse, because there will be shear failure, we can say. So generally the brittle failure is a shear failure, uh, shear failure due to excess shear force, and there is no ductility, because all of you know that whenever you put additional reinforcement or reinforcement in any concrete structure, it is a ductile in nature. But if the reinforcement is not sufficient, then it will be brittle failure and it will not give any warning. It will collapse immediately, as if it is, you might have seen in earthquake, and this, it collapse immediately. So this is not good design, and we should avoid such kind of design. That means there has to be some criteria which will take care of this part, and it will give enough warning to us. Now let's say same load is there now. So instead of that, I know that load is same. So load is same means increased load, 10 kilonewton per square meter, let's say. Even though load is more here in this case, when the load was there, then we have seen some cracks over here, let's say. So we have seen the cracks in the structure, and when you have seen the cracks, then definitely you can say get an idea there is something wrong. If there is a crack, means there is some overloading or something, we can say danger to this structure, and then you can evacuate easily, right? And evacuation is very possible, and then you can repair the structure or whatever structure, do the structural audit and so on. So it is giving enough warning to me before actual failure. So whatever our IS codes are there, whatever permissible stresses are given in the IS code, whatever is the design philosophy, that is limit state design, this limit state design in IS 456, it is taking care of this point, that we should get enough warning before actual failure. So this criteria is given in the IS 456, and whatever stresses we are having, permissible stresses, they are depending on this only, that it should give enough warning. So it's very important criteria as far as the design is concerned. Now I hope you have got the overall criteria regarding the design. So what is mean by design here? What is meant by design? Then what we do in design, how what we check in design: strength check, deflection check, that is serviceability. Then what is important parameter in design? Stiffness and size of the member. And stiffness means we can say moment of inertia, related to moment of inertia. Then these are the parameters which we should take into consideration in the design: cost effectiveness, beautiful, stable, serviceable, strong. Then it should give warning before failure. So these are the design important aspects we should keep in mind. So either you use steel material, you use concrete material, timber material, whatever may be the material, there is no problem. But these are the parameters. So worldwide, if you see people designing the structures, they will follow the same procedure. There is nothing different worldwide. So whatever may be the code, either Indian code or international codes, they are taking care of these parameters only while designing. So that means as we are dealing with the sizes of any member, that means then we should know the properties of the sizes or sections in general. And whenever I say design, the shape of the structure or shape of the member, so shape of either structure or member, shape means rectangular, circular, like that, or a small member we can say, like beam columns. And structure means in totality I'm talking. So shape is important of the structure member, or we can say this shape is having one good terminology, that is not nothing but a form of the structure, form. So this word is very important. This is generally important from the architectural point of view. So they use this form as a word, good word in this. So you might have seen different structures, so they are having shape. So you might have seen some bridges which are having arc shape like this. So there may be arc shape structures, then there may be suspension bridges with this. So this is a different form. We can say this is arc form or arch, we can say. Then we have seen the buildings which are rectangular in shape, high-rise buildings like that. So this is a rectangular shape or rectangular form, we can say. Okay. Then this is one form. Then you might have seen ESR, so ESR with staging, water tanks. I meant to say overhead water tanks like this. There is a staging and then there is a water here. So this is also one kind of form, we can say, as far as the structure is concerned. Then you might have seen stadium structures. So they are having some different shape. All right. Then you might have seen tensile fabrics. Do you know this word, tensile fabrics, which is used in roofs? Or we can say tents. You might have seen tents, cloth tents, we can say. So we use the tents also, generally used in circus. You might have seen circus, and they are having tents uh, for the temporary structure as a temporary structures. So all structures with different materials and different shapes. So material and shape. And shape. Shape means form. So this word is very much important because this form is having some peculiarity. So in design also, one of the important parameter I would like to say put into this point. So beautiful, cost effective. The shape which you are taking into consideration, shape or form, should be selected such that naturally it will take the load. And whenever say, see the shape as having let's say arch is having arc compression force in the structure. So let's say when I say it is a arch shape, this is RCC arch, let's say for example. Now what kind of forces comes into the arches? Mainly what is the force in arch? So generally compression. Okay. So there is a compression. So whenever you develop any shape, the forces change their behavior. So whenever I say instead of arch, if I put beam, let's say I'm preparing a bridge with using beam only. जो ये beam है. So there are two choices of developing the bridge. Now I am developing this bridge using horizontal beam. So whenever it is a horizontal beam, then there will be bending moment like this. All of you know it will bend like this, and the major force in this beam will be bending moment. So bending moment will be there in the beam or such kind of bridges, horizontal bridges. Now, if it is an arch, then you will see more important force in this arch will be compression, and bending moment is near to zero or very less. So I can say compression is dominant in this. So see the shape, as you change the shape, the behavior changes and the forces changes. So here in this horizontal beam, the bending moment is dominant and more, and in arch compression is dominant. So as you change the shape, the forces and behavior will change, and as the behavior will change, you should select the material accordingly. Okay. So selection of material should be there as per the form of the structure. So because the natural load and behavior is different, and then select the material accordingly. So if you select the material appropriate, then and then it will satisfy the requirements. So for example, if there is a compression, then one can think of putting RCC material here, because all of you know that there is a concrete, and concrete takes compression. So designing this arch using concrete will be good choice. Let's say to understand the concepts. I know there are steel structures in arches also, but try to understand the concept. Now there is a suspension cables here. You can see there are suspended cables. And definitely when I say suspended cables, they are tension cables. And not only tension cables, tensile cables, they are high tension cables. So these are the high tension cables. So I know I'm creating such a structure which will suspend this bridge, horizontal, this road and all bridge, horizontal slab we can say for a bridge. And I know that there are high tensile cables I am using. So the diameter of the tensile cable will be very less. So phi will be less, but the capacity will be more. Why capacity is more? Because they are high tension cables. As the diameter of the cable is less, it will look beautiful. So you try to understand. You might have seen, say, suspended bridges like this, our BKC and all, even in other countries also. So why the bridge structures looks beautiful? Because these are the small criteria they have considered during the design. So they select or they design such a sizes, they select such materials in the structure, so that in totality the structure looks beautiful, and it also uh, we can say justifies its functional requirements. So whatever functional requirements are there, they will be satisfied, and it will also look good due to its shape and selection of material. So this is very important point in design, and that's why form is very much important. Form, shape. So let's try to see simple examples to understand the concept of form and stiffness and all. Okay, so let's say you might have seen, so we use, so we are using scale, actually scale, all of you know scale, 1 feet scale or 6 inches scale. We generally use for measurement, drawing the sketches like that. Let's say this is a scale. So you know that there is a scale. Scale means ruler. You might have seen plastic rulers. Have you seen that? 1 feet का रहता है. 1, 2, 3, 4, 5, ऐसे 12. So 1 inch, 2 inch, 3 inch, 4 inch. Okay. So this is our plastic ruler or plastic scale, we can say. Plastic scale. And the plastic scale is having very less thickness. Generally we know that it's very thin. Material is plastic and it is very thin. And let's say I am putting this, I will just put on some support, this plastic scale. If I put like this, what will happen? This will bend. If you put the load on that, let's say, so it will bend. And if you also put the support to this, what will happen? Will it bend easily? आपको लग रहा है ये हाथ से? Let's say put this, you are putting the pressure by hand, let's say. So it will deflect, but will it deflect like this?
No, sir.
So as good as no, or it's very, very less deflection. You will not even see by eyes also. So I can say it's negligible deflection will be there. Negligible. Just see here it is very high. Let's say this deflection is something 10 mm, let's say, once you bend. And this deflection is almost 0.5 mm or 0.2 mm, let's say. Nothing. So why, what do you think? What is the reason behind this? What is the property which is resisting the deflection?
Material
The material property is not the real means. Still more appropriate to what is the thing. So you know, whenever I say I place the scale like this, the cross section of the scale is like this. Okay, you know this width is there, and this cross section is like this, vertical. Okay, so there is a deep enough. This one is deep enough in the direction of, we can say, load. Okay, so in this case the depth is more. In this case depth is very less. ये बहुत ही कम है ना, and that's why it is bending. And if you see here, this depth is quite large, so it is bending very less. So actually this is nothing but this is happening because of more stiffness. So not here, let's say. So this is having less stiffness, this orientation, or I can say it is a less moment of inertia, less I moment of inertia. Here it is having more stiffness, that means more I.
I.
This is the property, due to that it is happening. We can take one example. One more example, smaller example. समझो same kind of. So these are the support, and let's say this is a steel plate. Okay, steel plate, and we are putting this plate, let's say ऐसे कैसे तो है. So this is your steel plate. And this is my एक मिनट थोड़ा अच्छा sketch. So this is your support, and this is your steel plate, we can say. A thin sheet, we can say. The thickness is hardly 1 mm. Okay, 1 or 2 mm. And now you are putting load on this. So what will happen to this? This will bend because thickness is very less, and you know that if the thickness of steel is very less, steel sheet, we can say, metal sheet, and this will bend. Let me show a little more. It will bend more. So I'm using the same steel material and putting the load here. So there will be load, and it will deflect more. So why it is deflecting more? Yes.
Moment of inertia is less.
Yes. So moment of inertia is less, and that's why it is deflecting. So if you want to reduce the deflection, what you will do?
Increase the depth.
Yeah. So increase the depth, but generally you know that if you want to use this for any functional purpose, functional means for any reason. See this, I'm using only 1 mm sheet, and you might have seen our roof structures in steel structures. So they are also made up of sheets. But do you see these kind of flat sheets? Have you seen such a flat sheets in roof structures? देखा है क्या? Industries में देखा होगा ना? So we generally don't have that kind of flat structures. But we have, let me, so we have such kind of structures actually. Corrugated sheets, right? Now let me draw this. I don't know. ऐसे कुछ तो दिखेगा. Corrugated sheets. Have you seen the corrugation sheets
Yes, sir.
in industries?
Yes,
ऐसे कुछ तो
sir.
रहते हैं ना? And this is your support, then this is your support. Now what will happen? So will it bend like this? What do you think? So I'm using the same thickness, 1 mm thickness only, 1 mm thickness sheet, but now I have created the corrugation like this. And let's say this depth of the corrugation is something, let's say 5 centimeter, let's say 5 centimeters depth of corrugation. So if I draw the section, it should look like this. The thickness of this sheet is 1 mm, but the depth of this corrugation is 5 centimeters. Let's say. Now will it deflect more?
No.
No, sir.
So the less deflection, I would say less deflection. And we know that whenever there is a less deflection, that means moment of inertia, I is more. In this case, deflection is more. That means I is less. Correct. Now why I got increased? So what is the meaning of I in general? I'm saying. Don't ask, give me the formula if you don't know. But what is the peculiar point? That is the moment of inertia. So yeah, you can see this corrugated sheet.
Rotation about a particular axis.
Yeah, so moment of inertia, the word is very important. So many times we have the meaning within the word only. Moment of inertia, moment of inertia. For example, we can say resisting the moment, because inertia means not allowing to the moment. So it will not allow for the moment, or to rotate rather. Moment means rotation. So if that shape is not allowing to bend, so that rotation, we know that whenever we put load like this, it will bend. Bend means rotation. Rotation means we can say causing moment, and it will resist the moment. So whenever I have section, and it's a section property, so you can understand here this ruler scale is not bending because depth is more. That means its moment of inertia is more. So generally moment of inertia, we can say, if you arrange the material in a such a way that during its cross section, let's say you are having one material, ऐसे कुछ तो material है. Let's say, let me take arbitrary shape first, like theories. Let's say this is your shape, and then is one more shape that is like ऐसे कुछ तो shape है एक. Okay. So you will see there is a mass here, mass of material. यहाँ भी mass है. All is mass means you know that it is a material. If it is a concrete, then it is a concrete, whole concrete. If it is also concrete. लेकिन क्या हो रहा है? Whatever is the neutral axis about which it rotates or bends. You know that whenever section bends, there is a neutral axis. Whenever we see these beam sections, yeah. And if I try to show the bending, say beam sections, so you know that during the neutral axis, it will not change any its shape. So
Yes,
you know
sir.
that in compression zone, the length will shorten of this fiber, and therefore it is a compression. And in tension zone, this length will increase, and therefore there is a tension. But you will see that neutral axis doesn't change its length. That means there is no force. There is no force
Yes,
in
sir.
neutral axis, right? So that is the meaning of neutral. But you will see that there is a material here and there is material here. So if the material is more away from the axis, neutral axis, then we can say moment of inertia is more. So in this case, who will have moment of inertia more? I1 ज्यादा रहेगा या I2 ज्यादा रहेगा?
I1 will
I1.
have more moment of inertia.
Because the mass is located away from the neutral axis enough compared to this. See, let's say the area is same, total area is same. ये area और ये area both same है, लेकिन इसमें mass मेरा near to the neutral axis है, इसमें away from the axis है. And if this is the case, you know that if you try to bend this section, it will not bend because it's moment of inertia. We can say any, theoretically speaking, it is a property, or we can say this mass I can theoretically write as moment of inertia is nothing but something directly proportional to the area square, or we can say mass square. First, let me say at mass square, and for geometrical shapes we are dealing with, let's say A is moment of inertia is proportional to the area square. Okay. In general. So if you want to increase any moment of inertia of any section, what you want? You should keep the material away from the neutral axis as far as possible. Okay. So let's check it out. How we generally, we can say, optimize the material within the in design whenever we select beam sizes, column sizes, or whatever means. So I will show you that. So got the moment of inertia concept. Now let's see what happens. Let me take one example, a simple example. Let's say I have a beam, just for your comparison purpose. So if this is the beam, and let's say I am supporting this here, and the span is same, let's say L, and the cross section of the beam is like this. Let's say this dimension is 10 and this is also 10. Okay. And let's say I put some load over here, and this area of this cross section is nothing but 10 into 10 is nothing but kitna aega 100. Whatever unit you choose, centimeter, mm, whatever. I'm just taking unitless for the time being. Okay. If you take centimeter, let's say it is a centimeter square, 10 cm, 10 cm. And now what will be the moment of inertia for this? So for rectangular shapes,
So BD
formula
cube by 12.
BD cube by 12. So if it is a B and this is, we can say D. So direction is important, how the load is applied. Then D is like this. It depends on the load direction. So BD cube means 10 into 10 cube into, divided by 12 will be something. So this is the number. Moment of inertia is 833. Let's say cm cube. Okay. Now here the area is say. So now there is one choice. Instead of this beam, I will do one thing. Let's take. Let's increase the depth by 2 times. For example, the
20 and 5 we can take.
so for keeping the same area, let's say we are trying to use the area same. So I don't want to change the material area or material volume, we can say. I don't want to change this, but I want to change the size only. So let's say I will increase the depth and decrease the width. Okay, so ऐसे करना है मुझे अभी. And let's say this width is, I have just done that example. अभी मैंने क्या किया यहाँ, let's say I want to do this B as 0.707 B. This is my B, and this is my D, which is not nothing but 14.14. I'm just taking. See, you can see here, the depth is double than the. See, D is nothing but 2 times B. But if you calculate the area will be same. 0.707 into 14.14 will be nothing but 100 cm square. Okay. Are you getting?
Yes, sir.
So the
Yes,
area
sir.
is same. I'm keeping the area same, but I have changed the dimensions. So I have increased the depth such that it is 2 times the B width. Now if I calculate the moment of inertia, BD cube upon 12. So let's say B is how much point? So it is should be 7. 7.07. Okay, so B should be 7.07 into 14.14 cube divided by 12. BD cube upon 12. So it will be something near to 166 cm. It's not cube, it raised to 4. Don't forget the dimensions. Should be raised to 4 because B is in centimeter, D is also cm cube. So it will be
Yes,
cm.
sir.
So moment of inertia is in cm raised to 4 or whatever unit raised to 4. So this is the moment of inertia for this. So material, see, area is same, 100 only. Here also, here also. And again, let's again change the dimensions. So I am decreasing the width. Let's say same length. But this time width, I am again reducing. जैसे ये कैसे तो width है मेरा. And the width is, let's say, 5.7. This B is 5.7. And this depth is, let's say, 17.3. So third times. So this, my D is here now, 3 times B. Okay. Area is same. If you multiply this 5.7 into 17.3, it will be 100 cm square only. Okay. So in all three problems, this is first problem, this is second problem, this is third problem. Area is same means the material is same. Your cost of the material or quantity of the material is same because the area is same, length is same. I'm not changing length also. Length and all are same. But only I'm changing the cross section such that I'm reducing the width and increasing the depth. Now here the moment of inertia will be again BD cube upon 12 will be, the number will be 2498 something cm raised to 4. Now you see here, this is your third case, this is your second case, and this is your first case. What is the moment of inertia? Here it is 833. Here it is 1666, and here it is 249. So for the same material, the moment of inertia got increased. Okay. That means we can say if the rectangular shape is there, you can increase the depth of the section for the same area of cross section and reduce the width. Then you can increase the say moment of inertia, and it will help you to, what is the use of this? So if the I is more, the load capacity will increase. Yes or no? Load capacity of this section will increase. For deflection क्या होगा? So I can say I is not I, let's say load is proportional to moment of inertia. As moment of inertia increases, load capacity increases. And second thing is, if moment of inertia is more, deflection क्या रहेगा?
Less.
Less. That means I can say delta is inversely proportional to moment of inertia. So if you want to reduce the deflection, increase the moment of inertia. If you want to increase the capacity, that means we can say in totality, more moment of inertia is a good suggestion. But whenever you say more moment of inertia, what is the best choice of increasing the moment of inertia? Will you increase the width? Because you know that in BD cube upon 12, B is also there. So if you increase the B, I will increase or not?
Yes, sir.
But if you increase the D, it will
It will
increase
have,
a lot.
yes,
D
sir.
cube, it is a D cube. So it is always better if you change little depth of the beam or columns, the moment of inertia gets increased. So always whenever you have a choice of, we can say, changing the moment of inertia, change the depth first. Because if you change B, it will unnecessarily increase the cost because you will not get that. Let's say इसको बढ़ा दिया रहता तो क्या होता था? Let's say instead of 10/10, if I increase, ऐसे किया समझो मैंने अभी, these two problems are increasing moment of inertia. Let's say instead of this, if I do, ये ऐसे करता हूँ मैं समझो. Okay, ये है मेरा problem. And here what I am doing, I am increasing the D as 14.4. ये 14.4 है 14 and ये मेरा 7.07. Area is same, I know, 100 cm square. But moment of inertia क्या आएगा? BD cube upon 12, which is nothing but B is 14.1, 4 into D is 7.07 cube upon 12. अभी इसका कितना आएगा moment of inertia? निकलना पड़ेगा ना.
416.
416. Okay, I'll write it out directly. 416 cm raised to 4. Now he's here. Even though you are increasing the width, it is not changing. But here you are changing the depth for the same area. ये बहुत बढ़ रहा है. It is almost double. So always changing the depth or increasing the depth is a good choice for moment of say increasing the stiffness, load capacity, and all. So whenever you get a chance to change the rather if you are your deflection criteria is not satisfied in say building, समझो आपने एक beam design किया and the deflection is more, so what you will do?
Increase the depth.
So increase the depth. So that is the only way. Increasing the depth is a good choice. बहुत बार ऐसे होता है कि the architect forces you to reduce the depth due to their problem. So what you do generally, you increase the width, but many times you don't get much the benefit out of that. So stiffness and so this was with respect to rectangular, but in steel structure, if you see, so instead of the same problem, but I will consider the steel structure problem for easiness. So steel is very costly material. All of you know, very costly compared with even concrete. So if that is the case, you should smartly use that material. Otherwise, generally steel structure cost is very high. So let's say it is your steel structure, and this is a solid square, we can say, solid steel material. Okay. Solid rod, square rod, let's say. So this is having area A, say, for example, and this will bend for this span and due to some loading, whatever. Then if you want to increase the moment of inertia, what we have discussed that you can decrease the B and increase the D. So in the second case, but in that case, we cannot do rectangular shape because in steel structures, you might have seen the sections are not rectangular mostly. So what is the choice? Let's say area is same. Area is, let's say, 100 mm square. I don't know. कुछ भी ले लो. What I will do,
I section.
so I will use I section, let's say. Okay. So I'm using this I section. Now, as we have already discussed, whenever I put my mass or area away from the neutral axis. So here, what was the case? Let me take one small number only for, don't look into the practicality of the number, just concept, try to understand. Let's say ये हमारा 10 mm है समझो. Okay. Now here I am increasing this depth to, let's say, 50 mm. Okay. For easiness, and then width, say width should be 10 mm, let's say, and this thickness also 5 mm something. What I am doing, I am putting more mass away from the neutral axis here. Total area is same, let's say 100 mm square, I don't know. So this and this area is same, but this mass is arranged away. So in the flange area, I have more material. So flange area is more, let's say. So have you seen the section sizes in steel table before? You will see the thickness of flange is more. कभी भी देखो steel table में.
Yes, sir.
EF is more. Okay. So if you calculate the area BF, this width of the flange, and EF, if you multiply, the area of the flange is always more. So AF is more, and this web area of web is less. Okay, that means thickness of web is also less, because I want more mass away from the neutral axis. That means I want more mass in the flange section, and that's why these standard sections are developed, IS standard sections. Like I sections. Then we will again see. So there is one more choice where, so now you can understand by, you can look at the moment of inertia. So the main property in any steel structure section is the moment of inertia. So there is one more choice by which you can develop that section. So you can have I section, I say angle भी लगा सकते हैं इसको. This, let's say this is one plate, then I am putting angle over here. Then I am putting angle over here. So you can see the depth is more here, and I have more mass here. I am adding angles at this point, and the mass is away from the neutral axis, means the depth is more. So this way also we can do the sections in shear structures. Then you have seen channel sections bhi dekhe hai na aapne. So in the channels also you'll see you'll say that the flange area is more. So ऐसे अगर देखा तो ऐसे दिखेगा आपको. See, flange thickness is more, correct? Or flange area is more, and web area is less, because I don't want much mass in near the neutral axis. So again, you will see the same thing. So these are the shear sections available where the moment of inertia is more, because we are utilizing the property of the section. This is the property of the section. And that is the real beauty of design actually. As a structural designer, I would say the real beauty is how you are utilizing the properties of section, how you are utilizing the shape of the structure, how you are putting the material at required location as per the forces. When you do all these things in totality, then I can say that you are a good structural engineer and you are really, we can say, have understood the art of the structure. So that is the important thing. And whenever you see these sections, always create questions. Ye kyun hai? Then why there is a curvature like this? Why there is a curvature like this? Why thickness is more? I know that you may not find answer every time, but at least create questions in your mind or write down in your diary. Slowly you can learn and gain the knowledge regarding this. I don't want to answer these questions, but create questions like this. So this is also one of the section. Then you might have seen so rectangular tubes or square tubes. Steel structure में बता रहा हूँ. So this kind of tubes. So this is a hollow portion. Yes. This is your neutral axis, and this is your hollow portion, and this is your steel part. So ये मेरा steel part है समझो. This is your steel. Hollow, square, rectangular hollow sections. So here also, yeah, I'm putting more mass here away from this. There is one more peculiarity of having this actually. The moment of inertia is more. So you'll learn that in steel structures. I don't want to go into that. For the time being, let's say moment of inertia is more for this section. Any other sections you have seen?
Two channel section back to back.
Yeah, two channel sections back to back, correct. So generally we use in steel structures column design. So समझो ऐसे रहता है. It may be back to back or front to front, whatever may be the choice. Either it can be like this. Okay, so this is channel one channel, then this is second channel. ये built up column. Let's say I'm discussing built up column first. So this is your column section. These are the plates. ये plates है. And then there are two channels. And this is your neutral axis. So this is also built up column using two channels. You were saying back to back. So that will be something like this, na? Or do you want to say that back to back or front to front? Back to back means we can
Back
say
to
it is
back. Yes.
yeah, back to back means as good as I section.
Yes, sir.
As
That's
good
what
as
I
I
am.
section. Yes, yes. So this is also here also you have more mass here because flange area is more. This one. So these are the sections. Then in even we can say in Gantry girders, you might have seen there is a I section and there is a capping channel over the I section. So like this, there is I section and then we provide capping channel. So moment of inertia at the top portion or section modulus at the top is more. So we get more section modulus at this point. So moment of inertia for rectangular section is BD cube upon 12. The formula for this is for rectangular section only. And Z means section modulus, which is nothing but I upon Y. Y means this. If it is D, total depth is, let's say, D, then I can say this Y is nothing but D by 2. Similar to rectangular section. So I is how much? BD cube upon 12. And Y is क्या है मेरा? D by 2. So D and यहाँ 2 लेता हूँ मैं. So what is the value of section modulus? BD square upon? So generally BD section modulus is BD square upon 6 for rectangular section, and whatever unit you take, cube, cm cube. So moment of inertia is cm raised to 4 and moment section modulus is cm cube, either cm or mm raised to 4, whatever unit you use, mm cube like this. So these are the two important properties in design. Now again go to our RCC design, general understanding. So let's discuss the philosophy of RCC design. So let's take one example of beam. RCC beam is there. Now first we'll try to understand the concepts before any design. Let's say we have and there is a load on the beam, UDL. So due to UDL, what will happen to this beam? क्या होगा UDL से? Let's say it is a simply supported beam. So this will deflect, or I would say this will bend. And as it is bending, there will be bending moment. Yes or no? Bending moment होगा ना उसमें.
Yes.
And what will be the bending moment diagram? Let's say, let me draw it at the center first. So the bending moment for simply supported beam is like this. So there is a M.
WL square by.
So maybe WL square by 8 something. यहाँ कुछ तो moment आएगा. And so you will see that bending moment is maximum at the center. यहाँ कहाँ तो maximum, correct? So as it is bending, and see, you know that there is a tension here. So you can say that if I consider one element at this point, yeah, after bending chal raha hai mera. So if I consider the element here, so what is going to happen there? We know that there is a tension. So whenever I say there is a tension, means here there is a tension, huh? Because this deflection shape I'm just showing for just exaggerated shape, the deflection. So there will be tension here, yes or no? Now let me remove this first. Now, due to the bending, there will be bending moment, this bending moment, and due to bending moment, all of you know that there will be compression here. यहाँ compression रहेगा, and यहाँ tension रहेगा. Now let's say this is our concrete material, right? And all of you know that if it bends, what will happen? Bend होने के बाद क्या होगा इसका? So let me show somewhere else actually, वो ज़्यादा आसान रहेगा. So it will be, so it will bend. And at this point, let's say there will be a crack. Yes or no? ऐसे crack होगा ना concrete?
Yes, sir.
So the concrete will crack here somewhere. Because concrete cannot take tension, and there is a tension, and this tension is coming due to this bending moment, and the bending moment is maximum. So at the location of maximum bending moment, this crack will happen. Now if you want to avoid this crack, what you will do here?
Provide reinforcement.
Yes, so you will provide reinforcement here. So यहाँ कहाँ तो मैं reinforcement, because and what should be the direction of reinforcement, ऐसे कुछ तो चाहिए. Correct?
Yes, sir.
So how I am providing reinforcement in the direction of the tension force. You can see the direction of tension is like this. And that means my reinforcement direction be वही रहेगा. And then it will arrest this crack and it will not form the crack. So this is my reinforcement direction. So now here there is a compression. I already told you this is your neutral axis. Let me draw the cross section of beam. This is your neutral axis. So as I told you, this upper zone is compression zone. And in compression zone, concrete is okay. So concrete will take care of the compression. And here I am putting the reinforcement here. I can say I will put the reinforcement here. Yeah, voila. Now this is one point. So this is a tension. We are putting reinforcement for taking the tension due to bending moment. Now what other forces comes in the beam apart from the bending moment? क्या होता है उसमें? What other forces come in beam?
Shear force.
Shear. There will be shear. And shear force, you know, ये कैसे निकालना? Let's say this is your column, something column or wall, whatever you want to say. And there will be shear due to the load, W per meter, let's say. Shear diagram, I think all of you are now comfortable to understand. ऐसे कुछ तो रहेगा triangular shape.
Yes,
You can
sir.
see that shear value is more near the support. समझ में आया? So the value is more near the support. Now if you see the shear cracks, so as you go near the support, you will see near the support, let's say the beam will crack like this, something like this. ऐसे कुछ तो crack होगा. Okay. So here actually due to the bending moment, this was vertical crack here. Here you have seen the crack which was vertical, and here you'll see that it is a diagonal crack. And this diagonal crack is why it is happening. You know, whenever there is a crack, you can say that there is a tension because concrete cracks due to tension. That means there is a force, tension force in this direction. Convince हो रहा है क्या कुछ?
Yes, sir.
So whatever this tension is there, this tension gets developed due to the shear force. So this is our shear force V, whatever. So whenever we calculate this shear force, this is vertical shear force. It is causing this tension actually within this material. So I think you might have seen that principal stresses वगैरह सीखे थे आप बहुत college में. So if you consider this element, you will see that यहाँ tension आएगा उसका, and then it will crack. And the crack is formed due to the shear force. So what I will do, So if I want to arrest this crack, what will I do? This shear crack is due to this shear force. So in the direction, what I will do?
Provide
The
shear
Reinforce.
reinforce.
So there are two choices that in the tension direction, so this is your tension direction. So what I will do, I will put reinforcement in that direction. So there are two choices. One is that I will put the reinforcement like this. Okay, main reinforcement I can put. So this way I can put, and then I will again do this. So this way also I can arrest the tension, this tension direction, exactly diagonal. There is one more choice. You can see that this crack is propagating over here also. So I can at least arrest that crack by using horizontal reinforcement, which is arresting this crack. So this is a main reinforcement. So it is helping to arrest this crack also indirectly. And that's why you might have seen that whenever we calculate the shear capacity, we also check the main steel capacity, main steel percentage also, PT. So we calculate the PT, and as this PT is more, the capacity will be more for the shear reinforcement. So here I can put the main reinforcement here. So generally we call this as a bent up bars practically. Nowadays we are not providing these bent up bars unless and until there is an exceptional reason for that. General practice is not there. Previously, before 20, 30, 25 years, we used to use these bent up bars also to take the shear. So in our IS code, you will see to take the shear, we are providing bent up bars. So either you can provide bent up bars plus stirrups. So both clauses are there given in the IS codes. If you are using bent up bars, you can take that capacity also, and you can use the stirrups also. And if you are not using bent up bars, you can fully use stirrups also for design. So this is one of the case. So I hope you are understanding this. And if you are not providing this bent up bars, then you can provide vertical stirrups. So the crack is same. But in this case, I will provide a vertical reinforcement. So that we call it as a shear stirrups. So I say stirrups lagate na near to pass. So that they will resist the tension in this direction. Okay. The tension I say na, either I can resist the tension like this, or I say vertically. I need to take the component of that. So these vertical stirrups are taking this tension caused due to shear force. समझ में आया? So always keep in mind, whenever there is a crack, there has to be tension, and the tension should be perpendicular to the crack direction. So the tension may be due to bending, the tension may be due to shear, or tension may be due to any reason, shrinkage or whatever. In concrete, there are a lot of reasons of tension. It may be shear force, it may be torsion, it may be bending moment, it may be shrinkage, whatever. There are a lot of reasons by which the concrete cracks. So, but these are the two main components regarding RCC part. So bending moment and shear force. And we provide like this. So these are nothing but your stirrups. And why we are providing stirrups? To arrest this crack. Okay, now we will try to understand where to put the main steel, the different sketches for that. So as we have understood, in simply supported beam, I am putting this main steel here as per design requirement. मतलब moment से how to calculate AST वगैरह वो देखेंगे बाद में. So this I am main steel AST, and I will provide steel over here also, but it is not main steel. It is only to hold the stirrups. So there will be stirrups in vertical direction like this. So the stirrups will take care of the diagonal cracks. The red AST is my main steel, which will take care of my bending moment, this one, and the tension caused due to this bending moment. And the blue are only anchor bars to hold the stirrups. They are not carrying any force. Rather, we are not designing to carry the force. I can say it is an additional capacity, but we don't design that. We design only concrete for taking the compression in general. Now, this was for simply supported beam. Let's take one more example. Now we have taken those examples. मुझे सिर्फ बताओ स्टील कहाँ का डालना है. Let's say we have overhang, वो cantilever हमने किया था ना. Let's say it is a cantilever supported on these two supports, whatever it may be. So what is the bending moment for the cantilever? अगर हमारा UDL या point load रहेगा, whatever. तो जो point load है ये PP. So what will be the bending moment for this? So if you are not comfortable with this, I can again draw this mathematical drawing so that आपको ज़्यादा समझ में आएगा. ये mathematical है. We draw the beams by line, and then you may understand whatever I want to say. So what will be the bending moment diagram for this loading condition? कुछ दिमाग में आ रहा है? This is a cantilever and this is a point load, so it will be
inclined one,
and then again ये मेरा ऐसे कुछ तो रहेगा,
triangular,
and then it will be like this. Correct. So this is your bending moment. So as there is a bending, you will see that there is a maximum moment over here. I can say maximum hugging moment, and let's say this is maximum sagging moment. And below the point load, let's say, so here. So maximum tension will be here. यहाँ ऐसे कुछ तो crack होगा due to this bending moment. Again, here you will see that there will be crack like this due to this tension. This tension, let's say TH. This is TS. So this tension is created due to sagging moment below the point load, and this tension is created due to hogging moment. And that means as there is a tension, where you will provide the steel, कैसे provide करेंगे? कैसे करेंगे provide steel? तो यहाँ एक क्रैक आ रहा है मेरा और यहाँ एक मेन क्रैक आ रहा है.
one reinforcement at the lower portion in the first beam, and at
So
the
yeah,
second support we
maximum
will provide.
ideally speaking, I will require steel over here only, जहाँ moment ज़्यादा है. As you go beyond this, the moment is reduced. यहाँ maximum है, बाद में ये कम कम होते जा रहे हैं. So I can say either you can reduce the steel. यहाँ से steel reduce भी कर सकते हैं. बहुत बार क्या करते हैं हम, curtailment करते हैं. So curtailment, shall we discuss? Okay. So I will provide this steel. Just forget curtailment for the time being. Okay. So I will provide maximum steel at the bottom, near the center यहाँ. तो यहाँ मेरा ये दोनों मिला के जो steel रहेगा, that will carry this moment. So this total steel is for carrying. So the moment sagging moment के लिए जो लगेगा वो steel निकालेंगे हम यहाँ for this point. This is more. Now what steel I will provide at this top? क्या रहेंगे? यहाँ क्या डालेंगे? There is a compression here. You can see here from this point to this point, bottom में tension है and top में compression है. So I will provide only nominal steel here to hold the stirrups. ऐसे stirrups डालने के लिए. Okay. Now you see that there is a tension over here. यहाँ से यहाँ तक tension है, and then यहाँ से यहाँ तक है. So पूरा cantilever, यहाँ से ये पूरा cantilever, because the tension bending moment is full. So I will provide this steel here पहले तो यहाँ right तक जाएगा मेरा. Then whatever you see this point of counterflexure, it should be here and more than that. यहाँ से थोड़ा आगे जाना चाहिए स्टील. समझ में आ रहा है कुछ? So see from this point, extend this. Generally this is LD. LD लेते हैं हम आगे beyond the counterflexure. So this tension is nothing but AST for MH, this hogging moment के लिए, and this is for MS AST. So this will be the main steel. So whatever bending moment diagram we draw put the steel as per the bending moment diagram, that is the main steel. So this is also AST main for hogging moment. This is also AST main for sagging moment. And whatever blue color reinforcement I am putting, this is only anchor bars to hold the stirrups. So here I don't need any blue bars, anchor bars, because this main steel will take care of the holding the stirrups. But here at the bottom there is nobody, so I will provide this. So this is anchor bars to hold the stirrups. As there is a compression, so blue line is nothing but compression line. And we don't provide any steel in the compression zone because concrete is sufficient to take the that compression. Okay. So I hope you got this. समझ में आया सब? Steel
Yes,
कहाँ
sir.
डालना है?
Yes, sir.
Now let's take one more example. I know that you are now comfortable with the bending moment diagrams and all. So depending on the bending moment diagram, we are doing that. Now let's take continuous beams. Say,
बोर हो गया साला दिमाग खराब.
ये support say column or whatever brick, whatever you want to say. So what will be the bending moment diagram for this? These are my supporting points. Let me show me the ये point load भी ले सकते हैं, UDL चाहिए, whatever you want to take. क्या करेंगे? UDL लेंगे. चलो UDL लेंगे. Now it was point load previously. Now let's take UDL in this case. So let's say it is a UDL W kilonewton per meter. What will be the bending moment diagram? For UDL, this will be like this, right?
Yes, sir.
Yes, sir.
So you will see that at the center there is a maximum sagging moment here. Here also it is at the center maximum sagging moment, and at the exactly support it is a maximum hogging moment. See, we are only designing for maximum values. Please keep in mind in bending moment. So that means you can say due to this sagging moment there will be crack like this here somewhere due to this tension. Then you will see due to hogging moment there will be crack like this. So there due to this tension developed due to hogging moment, and again here. Once you find out the location of cracks, main cracks I would say, bending moment cracks, then you know how to put the steel. Now you can see here this is the point of counterflexure. So let me यहाँ है समझो point of counterflexure. So if I extend this line, let's say this is your point of counterflexure line. Again, if you extend this line, okay, here is the point of counterflexure. Now you want to put the steel. बताओ कैसे बल लगाएंगे? So maximum steel should be at the center. And as there is a complete tension here, I will provide bottom tension here. So let's provide the steel like this. And I will provide here more, means at the center moment is more. So this is the design for this. Now top, you don't need ideally any, you can say, but to hold the stirrups, I want this blue color. Now there is a crack over here. So I need main steel here. whenever I put main steel, it should pass beyond the point of contraflexion. So this is your point of contraflexion, means zero moment. So your reinforcement should extend beyond that also. So generally the value is LD. थोड़ा then, so this is for this MH, this AST. Then again here for MS, I will provide this steel. And then blue color for holding the stirrups, anchor bars. And then there will be stirrups, whatever it may be. Now, generally, whenever we provide the stirrups, we know that shear force is maximum at the support. So the shear stirrups are closer near the support. Okay, ऐसे close spacing रहता है near the support. So if you see the stirrup spacing, it is closer like this, and then it is far more spacing between the. So you know the shear force diagram यहाँ हमने निकाला था. You can shear force is zero at the center. So whenever we design any shear force, यहाँ तक हम पूरा लेते हैं ये zone में. We are putting closer spacing as I'm putting. So if this is the case, let's put more closer spacing here for the stirrups. Till some zone, generally this zone is 2D. We will see in detail in RCC design and all in our upcoming sessions. High-rise building का start होने के बाद. So this is your 2D and यहाँ भी 2D closer आएगा. And then this is less. So this is more spacing here. Because shear force is maximum near the support, you can see the value is more here and it goes on reducing till the center. So this is for continuous beam. Anybody having questions here? समझ में आ रहा है सभी को?
यस सर. सर
हाँ बोलिए.
कंटिन्यूअस बीम में सर हम लोग डेवलपिंग लेंथ सर सेंटर पर आ रहा है. हम लोग
सेंटर पे
सेंटर पर
मतलब
डेवलपिंग लेंथ नहीं ना देते सर. ओवरलैप जो ओवरलैप कर रहे हैं हम लोग जो यहाँ.
नहीं यहाँ बोल रहे क्या आप?
नहीं नीचे से नीचे.
हाँ यहाँ क्या? हाँ
यहाँ सर ओवरलैप सेंटर पर हो रहा है.
यहाँ
हाँ
नहीं, ये मेन रेड स्टील में जो मेन स्टील है ये ना, ये पूरा है विदाउट लैप है. हाँ
अच्छा विदाउट लैप है.
this is without lap. This
Okay.
red bar is without lap. See, the important point is whenever there is a maximum moment at that location, don't provide any lap. It should be straight. So यहाँ से यहाँ तक red bar straight है because maximum moment तो यहाँ है. You cannot lap at this point. Okay.
Okay.
Now these blue bars you can see they are lapped, but blue bars are not taking any force because they are in compression. Okay.
Okay.
So we need not to bother about the blue color, but red color is important because red is a main steel. Whenever I say main steel, it is at the maximum moment location. That is the main steel. And other bars are only just anchor bars. Now let's take an example of portal. समझो ये fixed है मेरा. And you know that for any point load or UDL, the bending moment diagram will be ऐसे कैसे तो रहेगा. So my bending moment diagram will be, if this is your loading diagram. So I think all of you know this triangular रहेगा कुछ तो ऐसे. If it is a UDL, then ये वो UDL की तरह रहेगा. बाकी तो same ही है. Okay. Now you can see here the bending moment is max here, ms max. Sagging moment यहाँ hogging moment है. So these are the maximum values. So यहाँ support पे sagging moment है center पे. So at the center there is a crack here. Then here also you'll find the crack somewhere here at the support. Oh, उल्टा निकाला. So I will provide the steel. कहाँ करूँगा मैं? यहाँ कर रहेगा मेरा maximum steel. तो ये nominal और ये additional center पे. So this will be my main steel for this sagging moment. Then you see कि above this point, let's say this is your point of counterflexure. यहाँ से यहाँ तक है समझो. यहाँ का तो है समझो. So till that. Then for this MH, I will require this steel like this. ऐसे I generally extend this beyond point of counterflexure. Now you can see here, this MH is transferred in column also. So due to this, as the joint is rigid joint, the moment will transfer in the column. That means to transfer the moment, whenever I say that the moment is transferred, that means the tension and compression gets transferred in the column. So where is the tension here? यहाँ है ना इसमें. Due to this hogging moment, there is a tension here. That means I need to develop this bar in the column also. यहाँ से ऐसे कुछ तो करूँगा मैं. Again here, ये bending moment है, and then hitting. So this vertical bar, which is we can say single bar without any lap. This is taking care of moment. This vertical will take care of moment MH in column, and this horizontal bar will take care MH in beam. So MH in beam, and this will MH in column, but they are same, or we can say continuous bars. So this is a detailing for this. So this is the main steel. Now there will be main steel over here also, don't forget. यहाँ भी रहेगा ना, यहाँ भी है ना tension, ये वाला अंदर की side में, and there is a tension here also in this side. So here in this side and here in this side, main steel. And generally we extend beyond the point of counterflexure. Okay, and then I will provide minimum steel. अभी ये जो steel रहेगा column का मेरा ये वाला. So generally we don't do like we cannot curtail in the columns like this. बीम में जैसे curtailment possible है वैसे नहीं रहता. Generally क्या करते हैं हम वही बार को आगे लेके जाते. I take this bar. I know that it is required till this length only, but I will take this till top. Okay, इसको भी मैं top तक लेके जाऊंगा. This is the overall detailing as per the analysis. Now, once you understand where to put the steel, where to put the stirrups, then we can design that. So in the upcoming session, next session, we will start with the design. What is meant by stresses and permissible stresses as per code and all these things. Okay.
Okay, sir.
So far, any questions?
Sir, when we design column, this bar consider होते हैं क्या?
हाँ, डिजाइन में होता है ना सब. See, we are designing the column for axial force.
मतलब
ये PU
एक्स्ट्रा बार
कौन सा एक्स्ट्रा बार? एक्स्ट्रा बार नहीं डालते उसमें.
ये
उसमें डायरेक्टली पूरा डालते. You are asking for column, na?
Yes, ma'am. Yes, sir.
So these bars we design fully actually. So generally कैसे रहता है? See, column design is based on PU, MUX and MUY by axial moment. Okay. So there are interaction charts and all this design philosophy for the column. And after the design, we get directly steel. Matlab, there are two criteria. Either you can put the steel uniformly over the section like this. ये मेरा column है समझो. So you can do like this. So all this steel is taking care of the moment, क्योंकि ये moment beam से आया हुआ है ना मेरा, this beam, both beam. So I am designing the column for these three forces together, and I check the interaction ratio. And through interaction ratio, finally I get the capacity of the column, and which satisfies or which takes care of all these forces coming from the analysis. तो ये पूरा रहता है, ये जो बार्स है ना ब्लू कलर्स के, they will take care of the axial load, they will take care of the moment. So ये जो moment मैं बोल रहा हूँ ना ये, so what force is coming in this column? There will be PU, there will be M, अभी MH है मतलब समझो ये MUX है. There will be other moment also in the other direction, which I cannot see in this frame. ये direction में रहेगा ना कहाँ तो, ये third dimension. So there will be MUY also. So we will design all this for these forces. होता है वो. But we don't curtail like this. This is not possible in column. Okay.
Excuse me, sir.
Yeah.
Sir, how we can improve our understanding concept means about this deflection and bending moment and shear force in the frames? I feel still difficulty in understanding how.
Till now, whatever I have told you during the training, have you understood, or is there still any difficulty? Whatever I told you, I am not asking some other questions. The questions which we discussed, or the
Yes,
training
I
which
can
we take.
understand. Yes, yes.
So there is a possibility that you might have understood only 80%. Let's say, for example, again go back and just think over it. The things which I have taken first. So don't go much away and distract to other problems, because whatever I discussed, they were only simple problems. Once you
Yes.
understand simple problems very well, then and then you can really solve the complex problems. So it should not happen that you don't know the simple problems and you are trying to think over the complex deflection and complex values. So don't go into that. So we are interested in simple beams, either fixed, simply supported, then continuous beams, then cantilevers, then overhangs, then frames.
I feel in frames more difficult.
Yeah, frames. Yeah, I know there is a possibility. So what exactly problem you are having? If you ask, I will definitely try to solve that.
In the last, yeah, in the last class, you show me more frames with deflected shapes, no? So that one I cannot go with that. I can't understand how the shape.
Yeah, so I really, this is the case. We cannot imagine. It is not something that to be imagined, but it is something that will behave like that naturally. So naturally, जो behavior वो आपको दिमाग में लेना है, and we have
So
to.
is there any tricks or tips to understand
Tricks
this?
means whatever I have taken, just first of all remember it and try to imagine whether it will deflect like that or not. Okay. So
Okay.
because see, there is no, the deflection will be like that only. So if you imagine something wrong, then it will not be a good, we can say, because our imagination may go wrong, but naturally it will behave like that. It should behave like that. So see, here there are two questions. I know that deflection problem are having issues whenever we solve the complex problems. This deflection is natural deflection. For particular load direction, there will be natural deflection. Natural, whenever I say that is, means it is not driven by your human mind. Not. So human mind cannot interfere in that. Not driven by this. Not. Please keep in mind. Now, even though you find difficult, don't try to solve it by your human mind. Whether can you look at it as a natural way, or can you prepare a model, let's say, for example, कोई तो एक छोटा रबर का मॉडल बना दो और उसको ऐसे कुछ तो फोर्स लगा के just try to see that. I'll check, मेरे पास ऐसे कुछ मॉडल रहेगा तो मैं दिखाता हूँ. See, I will just give you a guideline so that you can think. और बाद में यहाँ फोर्स लगाने के बाद you will see the deflected shape. जो मॉडल वो तो रियल है, रियल मतलब आई मीन से मटेरियल का बना हुआ है. आई एम नॉट इमेजिनिंग द मॉडल, इट इज अ लेट्स से रबर मटेरियल मैं यूज कर रहा हूँ, एंड देन आई एम उसको ग्लू किया मैंने यहाँ कुछ तो. When I glue it properly, then I can say it is a fixed support. I glue it here, and then I am pushing this by some your finger or whatever force, and then you look at the deflected shape. That deflected shape should match the deflected shape which I discussed. क्योंकि मैंने जो discuss किया वो भी मैंने invent नहीं किया. It is in the books and all research है मतलब. Now, if you want to see that deflected shape, real में क्या रहेगा? अभी software training is not yet done. You can try in softwares. And then look at that deflected shape and try to convince that shape, क्योंकि ये natural है, we cannot interfere. Just judgment लगा सकते हैं वो देखना. You have to see the judgment by looking at it. Okay, so that is the only way in frames or whatever complex structures are there. But at least you remember that the shapes for horizontal load, vertical load, point loads, UDL and all, for fixed supports, pinned supports, and because that is the basis for multi-story frames. Okay.
Okay, sir.
So I would say there is no, don't get desperate or rather say, I cannot imagine. See, you cannot imagine. No human mind can imagine this because it is a natural deflection and we cannot interfere in that. ऐसे कुछ नहीं है. But yes, once you understand this, let me see whether I have that. So see, whatever deflection shapes are there, I would say remember that first. But whenever you remember, please observe this carefully. Why it is happening like this, why it is happening like that. Okay, try to understand. I'm not saying you must understand 100%, but try to understand कि यहाँ ऐसे rotate हो रहा है तो ऐसे हो रहा है. And deflection, if you take some rubber material and if you put load, will it behave like this? And then try to remember all these shapes and for different loading conditions, for different supporting condition, remember this first, because this is the basis for multi-story. And then you can, once you learn the softwares, then you can model these structures in the softwares and then again look at the deflected shapes. Gradually वो develop होते जाएगा understanding. There is no hard fast rule because I know that this is not only your problem, this is problem of all candidates, all students. Okay.
Okay, sir.
सभी
So will
लोगों
you
का
share?
problem है.
Okay.
I'll do one thing. I'll share the deflected shape of frames and beams
That could be
from
better.
reference
sir.
book. एक book में जो रहेंगे ना वो screenshot में भेजता हूँ. Okay.
Okay. Okay, sir.
With respect to this learning only.
Yes, yes.
इससे ज़्यादा थोड़ा ये हो जाएगा. I'll share that. Okay, definitely. Just remember, and remember means first think over it and then remember. Don't remember blindly. और मैं मेरे पास, if I have any some model of rubber, I will check it out. I also tried it because I know that this question comes from the students, and the questions always come to me. How to understand this. So whenever also I started in the beginning of my career, I was also finding the same difficulty, how to understand this. So you might be knowing that people don't know how to draw the bending moment diagram because they don't know how to draw the deflection diagram. But they don't know why they don't know. So there is a big problem to the students or candidates, why they don't understand the bending moment diagram. This is the main question. See, they can draw bending moment diagram, what they know, what they remember only, but they don't know how it comes. So the basis is deflection. Now there is again problem, how to find out the deflection, because it is a natural phenomena. And Okay, whatever we have learned, that smaller problems, please study that.
Okay, sir.
Even in I think Mole's some on YouTube, I actually there is one toolkit which is in Germany or something, where they have prepared spring models, spring and steel balls. So they have created that structures, and once you apply the load, the frame, how the frame will behave, all these things are given in YouTube. Actually, it is also good, I think, model. It is in Germany, I think Germany or France, I don't remember, but they have shown that modeling. So they have created the frames using that spring arrangement and steel balls with fixed supports. Steel ball acts as a hinge support, and if you provide one 90-degree angle there, steel angle, then it becomes a fixed support. And then the behavior, how it changes, that all things are given. Mole structure, I think I need to check it out. Okay, just a moment. Okay, I'll just a moment. So this is a molar structural kit. Actually, it is. Now, can you see this? Hello.
Yes, sir.
So here
Yes, sir.
you can play this. Just a moment. अभी देखो. So they have created. See, understanding के लिए ये बना है उन्होंने. So the springs and then this steel balls. Steel balls act as a hinge support. See this. So if there is a bracing, what happens? Then now they are putting at 90-degree angle here. So this is a fixed support. They are creating this supporting arrangement, which will act as a fixed support. See this. Here also 90-degree. We know that at fixed we have a 90-degree. See this. Now, just I'm pausing this. Now look at this. Can you see this? ये ऐसे horizontal load निकाला था हमने, tension ऐसे था, then it was a. Can you see this behavior?
Yes,
sir.
sir.
Yes.
Again, here you can see here inside tension and then it is going outside. Now this we need not means हमें imagine नहीं करना, ये ऐसे behave कर रहे हैं ना. We are only observing it. So we are learning this through observation and not by imagination. There is two things separate. So I'm learning this through observation. I'm not imagining anything. I'm just looking at it and trying to understand it. So remove that block, mind block. Okay. यहाँ ये मोला structural model करके है. You will find different we can say videos there where that will help you to understand, because they are real time, we can say there. See this. Now look at, I think he will make it hinge at the bottom. So we have already solved that problem, bottom hinge. See this. Now see this. This is totally going here. And again. And now see the deflected shape and then again see the bending moment diagrams. अभी ये दोनों hinge है. See this. ये पूरा यहाँ है ऐसे. Tension outside दिख रहा है ना? or this got rotated here, but this is same, right?
Okay, sir. Yes.
Yeah. So refer this molar structural model and the videos given them by them. Okay, so thank you
Okay,
all. So we will continue our design part in the next session.
Yes, sir.
Okay, thank you, sir.
Thank you, sir.
Thank you
Thank you,
all,
sir.
and
Good
good night
night,
to
sir.
all.
Thank you, sir.